Hi, everyone. Welcome back to MAT1841. Apologies for being a little bit late today. The seminar went a little bit over right before. So what I thought I'd do today is I thought I'd first start off by giving a brief, so I'm not going to give this entire presentation. It's going to give the first third of it, which is going to be roughly the same length as I expect your project presentations to be. So basically, I'm going to talk a little bit about, and so hopefully this will give you a template for what I sort of expect out of you guys for your project presentations at the very end. So next week. And then afterwards, I'll take a little bit more time and actually go through some of the mathematics in detail, which I won't be able to prove because 25 minutes is not sufficiently much time to actually prove many of the things that to actually go through the math that we may care about. Any questions before getting started? Yes, I'm also recording today's lecture. So yes, but like basically this weekend, you guys have finished the stuff that I'm going to be officially assessing you on because I've already posted the problem sets. So this is just an example of a presentation so that you guys know what to expect. And also because like we're at the very end of the topics course. And so I'm just going to throw in random topics that I care about, or that if you guys have any things you care about, we can talk about that too. Okay, let's see. Let's get a timer going. So now it's now 3:19. And so this talk should be no more than 25 minutes. So expect about 20 minutes. Let's go ahead and get started. So this is 1/3 of a talk that I gave for the U of T CS theory seminar last week. I'm only going to be talking about the MinHash stuff, which is going to be related to the sketching that we did earlier on in the semester. And this is a paper that I published last year, which is going to be on reducing the space complexity of MinHash, which I think I alluded to when we discussed MinHash in that section, from log n space per bucket to log n space. So to get started, let's get started with just some genomics background. Well, what is sequencing? What kinds of data are we both looking at here? So the data that I'm interested in, particularly for most of my research, or for a large chunk of it anyway, is on genomic data. So these are some really long strings of A's, C's, G's, and T's. You can approximate it as some big long string of a 4-letter alphabet, 0, 1, 2, 3. And then, unfortunately, we're unable to read this entire string all at once. So what can we do? Well, our technologies are good enough that we can read short substrings at, roughly speaking, random locations in this big string. And we want to then figure out how to piece together an entire genome, so this entire superstring, from these small strings that we've read. And there are several different variants of this problem. One of them is the genome assembly problem. So given a string and a bunch of substrings, just recover the original string. Another one's the read mapping problem, figure out what location you're looking for. Given a string and another substring B starting at some position, figure out where it is from that original string, given the knowledge of the original string. We also have taxonomic classification. So given a bunch of strings and one substring of one of those strings, figure out which of those big strings it came from. And lastly, the one that we care about the most today, this genome similarity problem. So given two strings A and B, we're going to approximate some edit distance. And the way we're going to do this is by using k-mers. So given a string of length k, we're going to break it up into a bunch of k-mers for easy analysis. And there are a number of different ways you can do this analysis. One of them is to look at all of the k-mers in sequence. Another is to look at the set of k-mers that are present. So if you think of this as the sequence as a multi-set of k-mers, well, obviously, you have some repeated k-mers, and so you ignore those. And you can sometimes also, if you're doing a more machine learning-based approach, you might also want the counts of these k-mers to give it a bag of words with counts. But for our purposes, we're just going to think of it as a set because sets are nice and easy to work with. I think I mentioned in one of our previous lectures, the Jaccard index is just the a similarity between two sets that's the size of their intersection divided by the size of their union. Originally defined by a biologist to measure alpine ecosystems, it's used for a wide variety of things, including how closely related two genomes are. So if you can compute the Jaccard index between two genomes, then we'd be able to say something about how similar the two genomes are to begin with. It's not a perfect relationship, but it is a relationship that we are able to make formal. Now, so we talked a little bit about MinHash in class. We talked about minwise permutations. Basically, given some set A and B with some intersection, if you do a bunch of permutations of it, you end up with different elements that are the minimum under these permutations. And it turns out that the minimum under the permutations is in your intersection precisely with probability equal to your intersection size divided by your union size. And so if you could do these random permutations, then you could compute the Jaccard index and estimate it for the Jaccard index just by seeing how often your minimums match. Any questions so far? I'm flying through this pretty quickly, but that's because we already covered all this in class earlier. Okay, so now this is the part where it's slightly different. So let's think a little bit about what we need out of these random permutations. So random permutations are a little bit hard to come by, right? So, I mean, in order to do a random permutation of a big set, you need to know your entire set. Oh, wait, I am not sharing this, am I? Oops. So let me actually start recording this because I am not actually sharing my slides. Well, no one is on the Zoom right now, but presumably someone might come and join it a little bit later. That was an issue. So let's get stay co-host, no audio. So I apologize for anyone who's looking at this later, but you're going to miss the first couple of slides. Should have come to class. Okay, but anyway, so just to back up a little bit, we went through this slide, all of which we also did in our brief overview of MinHash and permutation. So you can go back and look at lecture, I don't know, like 8 or 9 when we did the background for MinHash. But now, so the basic idea is if you're doing these random permutations, they're expensive. And so if you had some random Oracle hash function that assigned a uniform random number for each of your items in your set, then you could come up with a permutation, right? Assuming that there are no collisions. But that is, of course, so you can use a random hash. You can try using a random hash function instead. So the classic example, which we discussed in this class, was h of the hash function of x is equal to ax plus b, where a and b are both from some finite field of prime order. Or from any finite field, really, but the easiest case is when they're from some prime order. And this has some nice properties. So for example, this has the property of universality, which is that two things don't collide with very high probability. It also has the property of k independence for k equal to 2 for our particular example up there. So you can treat each of these hash functions as independent random uniform variables for k distinct. So for x1 and x2 distinct in the case of a 2 independent hash function. But now this is actually not quite enough for a MinHash hash function. We want a couple of other properties for a MinHash hash function. One of them that we do want is we want this collision property. So something like universality, you want there to be not very many collisions. And of course, you can achieve this by just using O of log n bits for a standard hash function. So this is true for this is the easier of the properties that you want for a MinHash. The other really important property, though, which we didn't cover as much in class, is this property of minwise independence. And this is key to having MinHash work, which is that you want the probability that something is the minimum of some set under this permutation to be equal to the size of 1 over the size of the set. So you want every single item to have equal probability of being the minimum. And this is actually a much stronger condition than k independence for small k. So it turns out that you can actually prove that if k is big enough, then you're approximately minwise independent, which sort of makes sense, right? I mean, if you could pick k as big as your set, so if your k independence k is as big as the size of the set that you're looking at, well, then clearly you would get that property. But for k smaller than that, so long as k is big enough, it sort of approximates this minwise independence property. If you're familiar with other forms of hashing, there's a form of hashing called tabulation hashing that also has this minwise independence property, even though it doesn't have k independence. So this really is a different property than k independence or universality, and one that we didn't study as closely, but one that's essential for MinHash to work properly. In practice, of course, people just apply any standard hash functions, such as SHA-1, murmur hash, or whatever, and hope for the best. But you don't get any nice theoretical guarantees out of doing this. So now, the point of MinHash, though, is that what we need is, we don't actually need both of these properties. We don't actually need that all hash values are collision-free and MinHash and minwise independence. We only need that the minimums are collision-free, right? So we only need the property that minimums are unlikely to, we only need the property that minimums are unlikely to be equal to each other. Not that all hash values are unlikely to be equal to each other. And so somehow using O of log n bits gives you this much stronger guarantee that no two items are likely to collide. But we don't really need that. So can we take advantage of that to reduce the space complexity of our algorithm? And well, since I'm talking about this, the answer is going to be yes. that is something we can do. So how does that work? So my claim is that we can achieve this using order of log n bits for the range by using something like a floating point encoding. So this is going to be similar to the log or hyperlog counters that we discussed earlier, where you're able to use fewer bits by just storing the order of magnitude. That turns out that won't quite be sufficient. You'll need to do another couple tricks to make it all work out, but this is the basic idea. And so what we're going to do is we're going to consider an ideal random oracle hash function. So we're going to sort of ignore sweep under the rug the question of can we get minwise independence. I'm just going to assume that you have some ideal random oracle. You can think of this as just some other hash function that is minwise independent. And what we're going to do is we're going to try to take that hash function and then map it onto a smaller space and hope that we still don't get collisions. Well, if you had a random oracle, so this is going to make the analysis a lot easier, you could think of the probability density function of the minimum min hash of a set of n different unique items. And that's, of course, going to be given by n times 1 minus n to x to the n minus 1. So you can get the probability density function. We'll go over this a little bit more carefully in the moment when we go back through the math. And so you can get the joint probability density function of two distinct sets accidentally colliding in their minimum hash. And the way you do this is, well, your hash function is some series of discrete values, right? And so these discrete values are going to correspond to boxes of probability mass along the diagonal line, though they might be different sizes depending on what you're like throwing together, right? And so the collision boxes for standard log n bit minimum hash, all the boxes are the same size because what you're doing is you're just taking each of these. You're just saying, oh well, things collide if you accidentally have two different items mapping to the same value. And so that's something we don't want to happen. But now you notice that if you look at the PDF, the joint PDF, all the probability mass is concentrated in the lower left-hand side. Very little of that probability mass is over in the upper right of the unit square. And so why are we spending all this coding capacity on ensuring on collisions up in the upper right when all of our collisions that we care about are going to happen in the lower left, since we're only looking at minimums of a bunch of hash values and not just hash values in general. And so one way of doing this is we might think, oh, well, we care more about boxes in the lower left. So we want increased resolution down near the origin, but we don't need any resolution up near the upper right. And if you think about it, if your hash function was only storing the initial one position, so the position of the number of zeros before the leading one, then you'd end up with this series of sort of hash collision boxes. So if you'd be in the top right box if all you're storing is if you store a value of 1 for the position of the leading one indicator is in position 1. Well, what's the chance of that colliding? Well, the chance of that colliding is if both minimum hash values are at least 0.5. So that's the top right box. And if you're storing a 2, well, I'm not saying you're in the second box over there, where both minimum values are between 0.25 and 0.5. And so somehow we're trading off on these much bigger boxes in the upper right for collisions by saying, well, we don't really care about that, and so we're going to focus all of our coding capacity down near the origin. Does that sort of make sense? You should stop me if you have any questions on this. It turns out, though, that, and we'll see this in a moment, when we do the actual analysis, if you look at the number of collisions you get from trying to do this, it is way too high. So this does not work. But it sort of gets at the right sort of intuition for what we want to try to do, is we want to spend more of our coding capacity in the lower left than the upper right, and we can use this as a building block. So what we then do is we then divide up each of our boxes based sub-buckets. So we use, so we're coding for it by just storing a couple other bits after the leading one indicator. And so this is basically a floating point encoding. So you have some exponent, and then you have some mantissa. So this number here would be 2 to the minus 5. So this is coded in binary, 2 to the minus 5 plus, 2 to the minus 5 times 1.0001 in binary. And so you should think of this as scientific notation, coding in binary, coding in the floating point notation or something like that. And when you do this turns out you also have some fixed precision limit because you don't have an infinite number of bits that you're using to store the minimum value. But when you do this, it turns out that the number of collisions is fairly small, and it's going to be, we can bound it as less than or equal to 6 over 2 to the r, where r is the number of bits you're used to store the mantissa, and n is the number of elements in the bigger of your two sets, divided by 2 to the q plus r. And so this is going to turn out, assuming that, so basically the question is, how many bits do we need to store? Well, you notice that there's a 2 to the q term in the denominator for the second term, which is the only term that n appears in. And so because that's the only term that n appears in, in terms of the number of things that you can store, it's going to be doubly exponential in the number of bits that you're using to store the exponent. Sort of for the same intuition that log-log counters work in that way. And let me give a brief proof sketch, and then after the main part of the presentation, I'll actually give the proof. So the basic idea is that what we can do is we can overestimate the collision probabilities by dividing into 4 regions, covering and less overestimating the probability mass, right? So what we're actually trying to do is we're trying to measure the total amount of probability mass in the joint probability density function of all of these collision boxes. And you have some choice in how you want to construct these collision boxes, because those are basically what sort of compression or encoding you're putting onto the hash function, rather than just storing the full binary value. And our proof sketch is just going to be, well, we can explicitly compute. So given the computer, you can explicitly compute the actual amount of probability mass in each of those boxes. But you'll notice, well, how many boxes do we have there? Yeah, all the inside boxes. So how many total do you have? So in this case, we have 16, and that's because we have 4 boxes for the sub buckets, right? So you have 2 to the r buckets, where r is the number of bits you're using to store the mantissa. 2 to the r times 2 to the q, where q is the number of buckets that you're using, the number of bits that you're using to store the exponent. And so, but because obviously, like what you're saying is, we have all these different possible values. You have, when you're storing this value, you have 2 to the q possibilities for the exponent, and you have 2 to the r possibilities for the mantissa. And you're just looking to see how often those, and so for each possible value, there's some probability that your set A is going to have a minimum value that gives you that value, and some probability that your set B is going to have some value that gives you that value, right? And so what you're looking for is the chance that those match. And so in order to compute that, you need to compute the probability mass in each of those boxes. And so it's going to be 2 to the r plus q, which is going to get pretty big depending on what you're doing. And this is something that you can do explicitly, and you can for small values of q and r, but it doesn't allow you to tell asymptotics. And so what we want to do is we want to, in our theorem, well, we want to prove that, oh, sorry, where did my theorem go? Oh, there it is. So what we want to do is we want to prove some sort of asymptotic relationship of the number of additional collisions as a function of n. And we can come up with a closed form and actually measure these probabilities, but what we really need is we need some sort of asymptotic bound. And the way we're going to do that is we're going to divide it up into these 4 regions. We're going to overestimate the collision probabilities by dividing into 4 regions covering all the boxes. And since these are probability density functions, if you just overestimate the amount of probability, you're not going to mess things up too much. I mean, you might mess things up so that the probability is too high, but this gives you an upper bound on the probability of having a collision if you just cover it in all these different regions. And then all you have to do is, it's a simple exercise in probability to then, well, properly bound, then give an upper bound on the collision probabilities. Any questions about that? Okay. So I'm going to finish off the presentation part of this, so in about 20 minutes, by just saying that because I published this in a more applied journal, we did some experimental validation. So I have in my paper here, I proved it mathematically that this is true, but I also showed that when you run these numbers using simulations, they do match what you expect. So this is just basically saying that the proof is correct because we ran some experiments and the experiments didn't contradict the proof, which of course is not how mathematics works, but it is helpful when you are addressing 2 different audiences. So in this sort of paper, I was addressing 2 different audiences, both the more mathematically inclined, so I had proofs, and also the more experimentally inclined, where it could be like, hey, look, it actually does work, like in experimental results. And I think that about concludes my discussion of HyperMinHash. So basically, the idea was by using this more clever sort of compression of these hash values, we're able to reduce the space complexity from O of log n bits per bucket to O of log n bits per bucket, with some other minor terms that are caveats in the paper, which I'm not going to go into. Any questions about all that?
The error is actually lower than regular hash.
Oh, so it basically depends on what parameters you're using. So you can, the error depends so you guys use regular min hash for your, in one of the problem sets, right? And one of the things you would have noticed is that if you have more buckets, so if you use more hash functions, then the error decreases, right? And so here, some of the parameters where I control it for regular min hash with, these are basically regular min hash sketches using the same amount of total space. So if I have a HyperMinHash with 64 buckets and 4 plus 4 bits, 4 bits for the exponent and 4 bits for the mantissa, then that takes some amount of space, right? And then you can measure what the error is for Jaccard index with sets of a particular size, and for a particular Jaccard index. And then for minhash, I want to control if you're using the exact same amount of space. Well, you could use 64 buckets with 8 bits used for each of the values, or you could use 32 buckets with 16 bits. I mean, that still uses the same amount of space. And then the question was, is HyperMinHash really more efficient? And the answer is yes, because for a constant amount of space, HyperMinHash is going to have lower error because, well, you can either have more buckets or you end up being able to access the Jaccard index when your cardinalities get big. Okay, so that concludes my discussion of HyperMinHash, and hopefully that, that was exactly 20 minutes, roughly. And so that's sort of the level of the sort of presentation that I expect you guys to have for your in-class presentations. And you'll notice that I wasn't able to go in really deep into the math. I like sort of hand waved at some of the things you could do and like some of the sort of proof techniques. But really, it was just about explaining the sort of topic area and these things that I was exploring. Now, for your presentations, I know many of you tried projects that didn't quite work out, but like you can still talk about the sort of general area and the sort of techniques that are interesting in those areas. Any questions about the presentation? Like now would be the right time to ask about the presentation as well.
I feel like it's still quite dense, even though like you didn't dive into the.
Oh yeah, like 20-minute talks are hard. So like in my field at least, that is the standard length of a conference talk, is about 20 minutes. And so you just have to compress it all in and try to get as much of a flavor as possible. And then basically be like, hey, look, guys, there are lots of like, if you're actually interested, you need to go look at the paper because there just isn't enough time to actually go through it in detail. And yes, it is quite dense. But I am for one looking forward to seeing you guys talk about what you guys were thinking about, because it's always interesting to me. Like this is the graduate topics course, and what it means is that I'm also learning stuff from like the topics you guys choose. Okay, so now that we've done that, let's take a little bit of time and actually go through some of these proofs a little bit more carefully. So since this is my class, I get the luxury of saying I'm just going to spend all day on this, and we're going to actually go through and basically show you a little bit of what is necessary to do this proof. So I sort of gave a sketch there, but I didn't actually prove anything. So let me switch over to OneNote. And this is going to be HyperMinHash. HyperMinHash. Misspelled it, not a big deal. Okay, and so basically this entire proof is going to be just an exercise in computing expectations and probabilities. And so if we start off by assuming that we have A1 through AN, which are uniform random variables in 0, 1, IID, uniform random variables, and we have some set B1 through BM in the same thing. So these are IID uniform random variables. Well, these both correspond to an oracle hash function applied to disjoint sets A and B, right? So basically, if we had n items in set A and m items in set B, and we applied some oracle, and there was no intersection between the two, then we could just model it as n plus m IID uniform random variables on the interval 0, 1. And I'm going to use the interval 0, 1 to sort of approximate an infinite precision hash function, which is, of course, like slightly different than the formalism we used earlier when we were talking about hash functions where we're looking at finite ranges. But here we're going to assume it has infinite range. And then, of course, if you want to get down to a finite range, you just cut it off. You round it. And then what we're interested in is we're interested in minimums of these. So if we let x be equal to the minimum over I of the a sub I and y be equal to the minimum over all I of the b sub i's, well, we can compute these probabilities explicitly. So the probability that x is less than or equal to some value alpha is just going to be equal to the probability that all the values, that at least one of the values is less than or equal to alpha, right? So or or an is less than or equal to alpha, which is of course just equal to 1 minus the probability that a1 is greater than alpha, and so like that all of them are greater than alpha, which is equal to 1 minus, since these are all independent, probability of ai greater than alpha. So that product, which then implies that we can get the cumulative density function of x, which is equal to 1 minus x to the n. And this is how we compute the probability density function. So this is all pretty standard stuff. It's equal to n times 1 minus x to the n minus 1. Obviously for x in the interval 0 to 1 and 0 otherwise. And we also get PDF of y is equal to m times 1 minus y to the m minus 1, or the same regime. And so now, once we do this, well, you can look at, so we sort of talked about these things as collision boxes, and let me bring up these boxes just so that they're sort of visible here. So what we're interested in is these collision boxes here, right? So, and you'll notice that all these are boxes, and so it's pretty easy to compute those, because all you have to do is, so the probability enclosed in a square long diagonal, so if we let S be equal to S1, S2 squared, which is contained in 0, 1 squared. Oh, yeah, I guess one thing we should say is a joint PDF of x, y isn't just going to be multiplying them together, and 1 minus x to the n minus 1, m1 minus y to the m minus 1. And then the probability mass, I'm going to use mu of s, is just then going to be the integral over s1, s2 for both x and y of this probability density function. And of course, this is very easy to separate out because our x and y were independent to begin with. And clearly, if you're just integrating these boxes, you can separate out the integral for x and y. And this is just going to be equal to 1 minus s2 to the n minus 1 minus s1 to the n times 1 minus s2 to the m minus 1 minus s1 to the m, just by separating out the integrals. So that's all super easy. And so now, if we consider a HyperMinHash sketch with just one bucket, we're going to do the easy version, HyperMinHash sketch, one bucket, q bits for exponent, and r bits for mantissa. So that'll be something like 0.0001, 10, 10, 10, 111, whatever. So this here is going to be the value 4, and we can store that as 000100 if we were storing it in 6 bits, so 6-bit exponent or something like that. But of course, you can store any value from 1 to 2 to the q as possible exponents. And of course, we can have something like here, which is going to be our mantissa, so 4-bit mantissa. And we can combine these two things together, and we can encode as just, let's say, I and j. And basically what we're saying is that an accidental collision is when both of these values match, right? So that's exactly when you get an accidental collision. And so then all you have to do is then you just need to measure the when a particular set has these values. And so if we let gamma of nm be the expected number of collisions, So this is also just the probability of collisions because, of course, you only have one bucket. And so, but this proof generalizes nicely to multiple buckets, which is why I'm writing in this way. The expected number of collisions when size of A is equal to N and the size of B is equal to M are disjoint sets with a random oracle hash function. So then, for any possible coordinate I, J, well, when do they collide? So they collide precisely when when both X and Y are greater than or equal to S1 and less than S2, where S1, S2 are the boundaries of the boxes. Boundaries of boxes. Okay, so those are just these boxes that we see here. Clearly, you can figure out where these boundaries are, and so of course you can explicitly compute the total probability mass. And so thus, we know that the expectation of gamma, gamma, not the expected number, just the number. So expectation of gamma of NM is going to be equal to a double sum over I equal 1 to 2 to the Q and J equals 0 to 2 to the R minus 1, since these are the possible values of the mass in these boxes. S1 of IJ, S2 of IJ squared. But it takes a lot of time, as we discussed earlier. And it also doesn't give us any sort of asymptotic bound on how the space complexity of our algorithm. And so you can use a computer to do this, but it doesn't tell you anything theoretically. So now what we're going to do is we're going to upper bound it by covering it with bigger regions. So we're going to cover it with these regions that we showed over here. Oh, come on. So we're going to cover in these regions, and then we're going to upper bound that probability. And you have to be a little bit careful when you're deciding how to cover these regions. And what we're going to do is if we have, I'm going to let R bar be equal to 2 to the R and Q bar be equal to 2 to the 2 to the Q for simplicity. So those are obviously important because those determine the size of the smallest box, as well as the number of boxes within each of the bigger hyperlog regions. And then what we're going to do is we're going to draw out these boxes. So if we draw them out, of course, we have our big regions. So our big regions over here. And then within each of these regions, and we have our smallest region down here. And then within each of these regions, we have some number of boxes. And what we need to do is we need to figure out some way of covering all of these, and then such that we can bound the mass easily. And the biggest component here is we want to, so the sort of edges aren't that important, right? Because we can explicitly compute for some finite number of boxes what the probability of collision is going to be. So the important thing here is I'm going to draw a ray that starts out at the lower left and goes exactly along these boxes. And I'm going to end it somewhere around here. It doesn't necessarily line up exactly with those, but there's some ray we can draw that's going to precisely hit the tops and bottoms of the first set of boxes in each of the big boxes. And you'll notice that this ray has some problems. Like it doesn't quite cover the stuff down here because our smallest box is the same size as the next box. And so because we're not telescoping down infinitely, since there's some precision limit in the exponent. And also, we can't quite keep drawing the ray all the way up here because the ray then goes out of the bound between 0 and 1. And so our probability density function, you could draw it out further, but then you'd have to have a special case for what happens to the formula would just become a little bit more painful because you don't want to accidentally integrate in some negative values of the thing that we've defined as your PDF when it really should be 0. So we're going to do that. And then what we're going to do is then we're going to have a rectangular box up here, which is going to cover the remaining area, just a square box along the diagonal. And that's, of course, really easy to compute. We already know the formula for that. And additionally, what we're going to do is we're going to cover up a region that is just another box, another small array, but with both the top and bottom exactly parallel to each other for the smallest box down here. And then we're also going to include just the smallest box by itself. And you will see why this is all quite important. It's because somehow the smallest box captures what happens when you have too many terms. And so it's important for us to consider that one separately. But everything else, the probability of collision is going to be bounded in this way. And so now the question is, what is the slope of this ray? So this ray here, the top ray, is going to have y is equal to r bar over r bar plus 1x. And this bottom ray is going to be at the line y equal to r bar plus 1 over r bar x. Which then also, of course, means that this point here, where you stop, is going to be r bar over r bar plus 1. Okay, so all we're doing is we're decomposing our region into these nicely spaced areas. And then, well, we know how to compute the area of, the mass in that box, as well as in that box. The clever thing is going to be, what do we do about this ray? So I think that's all I'm going to have time to really go through. So what is the probability mass in this ray? Well, that's going to be a slightly more complicated integral, though still fairly straightforward. So you're going to integrate from from 0. So the first integral is going to be over dx, 0 to r bar over r bar plus 1, because that's this value up here. So we're going to integrate up to there. This ensures that we're always integrating over something that's valid for our joint probability density function. And then, of course, we're integrating from the bottom here to the top, because you're integrating over this set of y values. So that's going to be r bar over r bar plus 1x, up through r bar plus 1 over r bar x. And then, of course, just the probability density function, m times 1 minus y to the m minus 1. And now all we have to do is we have to upper bound this. And this is going to start off pretty easy, because you'll notice, of course, that there, in terms of the x dependence, you can sort of shift things around a little bit to make life a little bit easier. And this is going to be the integral from 0 to r bar over r plus 1. The first, you can integrate over, dy. You can integrate over y pretty easily, because that's just a single probability density function. We already know what the integral for that is. It's going to be n times 1 minus x to the n minus 1 times 1 minus r bar over r bar plus 1 x to the m minus 1 minus r bar plus 1 over r bar x to the m dx, right? So that's just because what we're doing, we're just using basically, well, the CDF there. So that's just the CDF of just the y variable. And then now this next integral is going to be a little bit more complicated, but we can notice that there is a difference of square. We can use a difference of squares formula to simplify this. So for 0 is less than or equal to beta, is less than or equal to alpha, is less than or equal to 1. We know that alpha to the m minus beta m is equal to alpha minus beta times the summation from I equal 1 to m of alpha to the m minus 1, beta to the I minus 1, right? And so this is just the telescoping thing. And so then this entire thing is less than or equal to alpha minus beta times m to the alpha m minus 1, if alpha is greater than beta. So we can use this inequality, and you notice that this alpha is greater than that beta, where we let this be alpha and this be beta. And you can, it's pretty easy to show that is actually greater. And then when you do that, this implies that the probability mass of the ray is less than or equal to the integral from 0 to r bar over r bar plus 1, n times 1 minus x to the n minus 1, and 2 r bar plus 1 over r bar times r bar plus 1, x m 1 minus r bar over r bar plus 1, x to the m minus 1 dx. You can rewrite this a little bit, and what you end up doing is you'll do an integration by parts. It's rather ugly, but you can do it. Integration by parts. And this is going to give you that this is less than or equal to 2 r bar plus 1 times r bar plus 1 over r bar cubed times nm over n plus m minus 1, which is less than or equal to 3 over r bar. Okay, and you can do the same thing. So the same sort of analysis lets you get that the mass in of the strip down here, so this black strip, and this was the ray. So that black strip is going to be have probably mass less than or equal to 2 over r bar, and you use the same type of analysis. You use the same difference squares formula, and it all works out. And of course, then you have the top right box. So the top right box, that's going to be, well, that's going to be really, really small. And that's something you can sort of see because you have very low probability mass up in there anyway. So we don't really care about that, but you do need to bound it. And that's going to be less than or equal one really, really ugly bound. I mean, really loose bound. It's going to be 1. It's actually much lower than that in most cases, but certainly that is an upper bound. And the lower bound down here, this is the most interesting box. This bottom left box is the most interesting one because that bound is actually going to be quite different. So that bound of the bottom left box is going to be less than or equal to n over r bar q bar times m over r bar q bar. And if we let n be greater than m, this is less than or equal to n over r bar q bar. And somehow this is the part that implies the log scaling of the number of bits that you need in the boxes. I'm not going to have time. So even with a full hour, I'm not going to have time to go through all of it. But basically, oh, sorry, not that one. So basically, once you do this, so you can compute all the expected number of collisions. But of course, when we were doing these kinds of things for sketching algorithms, we cared about both the expected number of collisions and the variance in the number of collisions, right? And so then what you need to also do is, well, you have then you also need to show that the variance of the number of collisions is not too high. And these things are almost independent. So the events that happen in different partitions are almost independent, but not quite. And so what you do is, remember when we had these almost independent things with like our random graphs, what you had to do is you had to decompose it into some part that was like, some part that was independent and then some other part that didn't really matter. And that's basically the strategy we use here, where we decompose C into one part that where we condition on this multinomial. And by doing this, you're able to show that the variance is actually less than or equal to the expectation squared plus the expectation. And so the standard deviation is about the expectation, which means that you don't have too many more errors than you'd expect. And from that, you're able to that basically proves the entire theorem. So that's all there is to it. And yeah, and I think that is all I'm going to have time for in terms of the actual mathematics of this thing. And hopefully that will also be the end of class. Next Wednesday, I'll probably talk about some other projects that I've done. I haven't decided which one yet, unless you guys have something you're particularly interested in which case email me and I'll look into that. So thank you all very much. I look forward greatly to seeing all y'all's presentations. If you have any questions about how to do a presentation or how to write a paper, I'm happy to look things over early. So if you send it to me early, I'm happy to look it over. But if you don't send it to me early, then I just have to mark what you present and send me at the end of class. So, okay, class is dismissed.
You mentioned the papers are due on the 8th, correct?
The papers are due, oh yeah, that's a good point. The papers are due on the last day of class, which is the 8th. I'm allowed to give you a 5-day extension if you ask for one, and a 5 business day extension. So, and I am willing to give you a 5 business day extension if you ask for it. You do have to officially ask for it, but assuming you do, I will give you a 5-day business day extension on the paper, which is also useful because I will be providing some amount of feedback and your peers will also be giving you some feedback from the presentations, right? And so like some of that feedback might be stuff that you should consider incorporating into your final paper.
We can also send you like on presentations like prior.
Yeah, no, like if you want to send me your slides early, like I'm happy to look it over and just like give you a sense of like if like what things you should hit and what things you shouldn't. Yeah. Okay. Take care. Bye.